So now in this problem, we are going to see another application of Arrhenius equation where we know the value of reaction rate constant at one temperature and we want to find out the value of reaction rate constant at a different temperature. But we do not know the value of the frequency factor, just know the value of the activation energy. Okay, so we will use the Arrhenius equation definitely that are seen here, k equal to a, that is the p exponential factor into e to the power minus e by RT. And the problem description, it is the homework problem 7 of chapter 3. The reaction rate constant Ka is given at temperature 300 Kelvin as 0.01 second inverse. And as we know, if the unit of reaction rate constant is time inverse, then it is a first order reaction. What will be the value of reaction rate constant at 400 degree Kelvin? So we know the value of Ka at 300 Kelvin and we need to find out the value of Ka at 400 Kelvin. And the information that is provided that the activation energy for this reaction is 6 kilocalorie per mole. And we need to be very careful with the unit because we have also the energy unit in the gas constant Rg. Right, so we need to be a little bit careful with the energy units. And it should be unified units. We'll see it in the next pages how we are dealing with it. So here we will use Arrhenius equation to solve this problem. We know the value of Ka at a temperature, let's say it is T1. Right, here in this problem it is 300 Kelvin, but let's name it as we are trying to formulate an equation. Let's say at temperature T1, we know the value of Ka and we need to find it our value Ka at a temperature T. The unknown value of Ka should be evaluated at a temperature T. So we will formulate an equation from Arrhenius equation. So for temperature T1, that T1 is known, the K1, for temperature T1, at temperature T1, the value of Ka1 is known. So Arrhenius equation we can write down as Ka1. That means that Ka at temperature T1 equal to A is the free exponential factor exp minus E by R T1. So this is the equation for temperature T1 and the value Ka1 is known. And we can write down another equation for temperature T. At that temperature, the value of Ka is not known. So as Ka equal to A exp minus E by RT. So at this T, the value of Ka is not known. So we can now divide equation 2 with equation 1. Right, if you divide equation 2, that is this equation with this equation, so we can write down as Ka divided by Ka1. Ka1 value is known, so equal to A exp minus E by RT divided by A exp minus E by RT1. So you can see that this A, the pre-exponential factor, can be cancelled out from up and down, and we may need to do the calculation for the exponential term. And I hope you can remember your exponential formula, right? So I should see. Okay. So the exponential formula is e to the power a divided by e to the power b is equal to e to the power a minus b. So we will apply this formula to solve this part, this exponential part of this equation. Okay, so now if we apply this exponential equation, so we'll have Ka divided by Ka1 exp minus E by RT plus E by RT1. Again, we can take common E by R in this inside the exponential term. So we can see that we can write down the equation K equal to K1 exp in the bracket E by R in the bracket 1 upon T1 minus 1 upon T, and the bracket closes. So this is the formula we can use. So Ka1 is known, T1, T is known, and we can find out the value of K. We do not need to know the pre-exponential factor to calculate K, right? So this is one of the way. Just the activation energy is required and the temperature and a known value of K at a temperature. That's it. So you can calculate any temperature the value of K. Okay, so now we solve this problem that we have here. Like at 300 Kelvin, it is 0.01 second inverse. And what is the value of K at 400 Kelvin? The value of E is 6 kilocalorie per mole. R should be in calorie per mole. It is 1.987 calorie per mole per Kelvin. So the units are very important for R and also for the E. See it right now here. So this is the equation to calculate Ka at a different temperature, right? T. So we just put the values like say Ka1, that is a known reaction rate constant. It is 0.01 second inverse. Then exp, the value of E is 6 kilocalorie per mole. So we put 6 into 1000 calorie per mole. We convert kilocalorie to calorie because the R value is 1.987 calorie per mole per Kelvin. So you can see this calorie and calorie unit cancels out. Mole unit cancel out. And then we have the temperature. T1 is 300 and T is 400. And the unit is Kelvin. So you can see that this Kelvin cancels out. Right? So the unit inside the exponential term is dimensionless. That's another way to check that everything is all right for your calculation. And the unit for your reaction rate constant will be the unit second inverse for this case. It is a first order reaction. So you'll get step-by-step calculations. The inside the exponential, if you do the calculation, it will become 2.516, and if you make it, it will become 12.37, and now it is a capital K somehow, so it should be small k reaction rate constant. And if you do the calculations, and it will become the new value at 400 Kelvin, it will become 0.123 second inverse, right? So very nice number, 123. Okay, so 0.123 second inverse, and we know that with the increase of temperature, the reaction rate constant will increase, and we know you can also see it here at 300 Kelvin it is 0.01, and at 400 Kelvin it is 0.123, right? It increases, so maybe our calculation is correct, right? So this is one of the way to calculate the value of Ka at a temperature, right? If we know the value of Ka at a different temperature, right? And try to remember this formula, and it will help us a lot in a future calculation things. Also in chapter 5, we will use the same formula time and again to evaluate the value of Ka, that is the reaction rate constant at a at the reactor temperature cases, right? And this equation has a great application. You'll see later on in reaction engineering. And thank you for this program.